As the Webb looks back at the beginning of things, we actually got a look at some incredible images. The James Webb Space Telescope, JWST, has shown something that goes beyond what we now know. Scientists and stargazers are interested in this new discovery because it points to a possibly massive event that could alter the universe to the point that we might be concerned. The discovery is so important that it calls into question why we are here in the galaxy. Will all we know about the cosmos eventually come to an end as a result of this revelation? Join us as we explore the most recent discovery of the James Webb Telescope and its potential to influence the universe, right on the verge of an extraordinary event that surpasses our current comprehension. The perceptible universe is where we begin our investigation of the edge of the cosmos. It's similar like looking through a window into the space beyond the cosmos as we know it. Everything that we can now see, measure, and explore with our telescopes and space missions is part of the perceptible universe. It consists of a group of familiar stars, galaxies, and other celestial bodies. Though the basic size and nature of the universe are still unknown, the conspicuous universe is essentially a slice of the entire universe, a bit of a huge, enormous pie that people can study and observe. The detectable universe is approximately 93 billion light-years wide. The 9.46 trillion kilometers or 5.88 trillion miles that light can travel in an Earth year is one of the variables that contribute to this number. The distance covered in a year by light, the universe's fastest substance, is known as a light year. The universe is thought to have existed for 13.8 billion years after the Big Bang. This indicates that light from visible space objects has been moving toward Earth for around 13.8 billion years. Accordingly, the visible universe is 27.6 billion light-years in diameter and 13.8 billion light-years in all directions from Earth. But according to Hubble's observations, space has been growing ever since the Big Bang. The visible cosmos has therefore been expanding. Objects that produced light 13.8 billion years ago at a distance of 13.8 billion light-years are now far farther away from Earth, at about 46 billion light-years, according to estimates of this expansion. This indicates that the observable universe has a diameter of about 93 billion light-years and expands more than 46 billion light-years in each direction from Earth. Therefore, when scientists say that the visible universe is 93 billion light-years wide, we are referring about an incredibly wide influence that began about 13.8 billion years ago. What we now call the continuing expansion began with this impact. In addition to growing, the cosmos has been accelerating since that crucial point. The speed increase appears to be driven by frustrating factors like as the enigmatic dark energy, which is pushing the boundaries of the cosmos farther and farther away. As the universe grew, matter started to form under the force of gravity. Particles were drawn together by this gravitational pull, creating complex structures like stars, galaxies, and ultimately planets like our own Earth. The visible universe grows by 1 light-year every Earth year due to the cosmos's continuous expansion. Light from distant objects is still reaching Earth at the same time. It's interesting to note that this indicates that as time goes on, we are witnessing an increasing amount of the cosmos. Even though we will never be able to see the entire cosmos from Earth, our field of view is constantly expanding. We can now find and observe far-off individual galaxies, clusters, and superclusters in the observable universe thanks to technological advancements that capture and study electromagnetic radiation outside of the visible spectrum. In this context, certain telescopes have proven useful, such as radio telescopes, X-ray telescopes, ultraviolet telescopes, infrared telescopes, and others. These wonders are now more widely accessible to the public thanks to the famous Hubble Space Telescope and James Webb Space Telescope, which have made it possible to observe the earliest stars and galaxies to appear in the observable universe. The universe, for all its size, is strangely empty. The closest star would still be about 2 soccer fields away even if our entire solar system were shrunk to the size of a quarter. We get an idea of its enormous scope from the fact that this huge vacuum spans within our own Milky Way galaxy, one of the billions in the observable universe. Why we can't simply see the entire universe might be on your mind. This constraint can be explained in a number of ways. Even though light moves through space at the fastest speed in the cosmos, it still takes time. This implies that we are effectively looking back in time when we gaze at far-off objects. An object's light has taken longer to reach us the farther it is from us. Seeing galaxies that are millions, if not billions, of light-years away is like stepping back in time and unraveling the history of our universe. But the universe's expansion is another aspect at work. Think about the dot-covered surface of an inflated balloon. As the balloon expands, the dots separate from one another. The same principle applies to the universe. As space expands, galaxies move apart. This expansion causes a change in the light that distant objects emit, called redshift. As a result of this expansion, things moving farther away cause light wavelengths to expand, changing to longer wavelengths that are typically seen as reddish. Because the universe is expanding, some celestial things eventually pass beyond a crucial distance called the cosmic horizon, where their light is too far away to reach us. It's not unexpected that we haven't yet seen the entire cosmos given these two important factors, the expansion of the universe and the path of light through time. Indeed, the basic properties of the universe continue to limit human view even with the most sophisticated telescopes and technologies. We need to explore these ideas a little further. The immensity of the universe is astounding. The distance that light travels in a year, which is approximately 5.88 trillion miles or 9.46 trillion kilometers, is represented by metrics like light-years. The Milky Way, our cosmos, spans almost 100,000 light-years. Proxima Centauri, the nearest star to our Sun, is located approximately 4.2 light-years away, even within our galaxy. We can see galaxies billions of light-years afar when we travel through space. This provides us with a window into the early history of the universe since it indicates that the light we see from those galaxies began its trip billions of years ago. Many people from a variety of areas have been interested in the enigma surrounding the edge of the cosmos and the pursuit of understanding its potential limitations or bounds. Three important hypotheses have surfaced, each providing a distinct viewpoint on the vastness of space, even though conclusive answers are still elusive. According to the first theory, there is no limit to the cosmos and it is infinite. The cosmological principle, according to which the cosmos is isotropic, its homogeneity and appearance are the same from every angle, is consistent with this notion. The universe has no boundaries and can expand indefinitely in all directions if this hypothesis is correct. Examining these hypotheses sparks curiosity in both philosophy and science. Our conceptions of space and its limitlessness are called into question by the idea of an infinite cosmos. However, a finite universe without an edge calls into question our understanding of boundaries and limits and raises the prospect of recurrent patterns in the fabric of space. With its parallel universes, the multiverse concept suggests the existence of worlds very different from our own, providing a rich field for investigation. If accurate, it might suggest that changes in fundamental constants and physical rules could result in completely new forms of existence, creating a world of possibilities that are beyond our current comprehension. These concepts are still speculative and elusive, though. Examining the edge of the cosmos is a difficult task. Given the size of space and the limitations of our current technology and observational capabilities, it is challenging to conclusively confirm or refute these beliefs. The search for the boundary of the cosmos has been an intriguing adventure full of hypotheses and contemplations. The James Webb Space Telescope, JWST, a magnificent equipment that sheds light on the riddles surrounding the universe's origins, stands out as a positive indicator. This amazing tool has the ability to reveal the buried history of our universe, giving us access to knowledge that was previously unthinkable. A technological wonder, the JWST was created especially to observe the cosmos with unparalleled accuracy. We can see into the origins of the cosmos thanks to its amazing characteristics. Massive galaxies from 500 million to 700 million years after the Big Bang have been found by the JWST. With diameters much bigger than anticipated for their age, these old galaxies defy predictions, according to new research published in Nature. Established hypotheses on the birth and evolution of galaxies in the early cosmos are called into question by these astounding discoveries. When astronomers first started using the telescope, they anticipated seeing tiny, young galaxies. Rather, they were taken aback by the discovery of these huge, amazing structures, which have changed the story of cosmic evolution. These ancient galaxies' growth is especially remarkable and defies accepted wisdom. The study's chief investigator, Dr. Lear, said these cosmic giants have developed to a degree similar to that of our 13-billion-year-old Milky Way. This discovery casts doubt on our knowledge and provides fresh insight into the early universe's galaxy formation process. Furthermore, the JWST has captured light from the first stars in the universe, which allows us to travel back in time to when the universe was only 300,000 years old. The characteristics of these early stars, referred to as population 3 stars, are quite different. They originated when there were very few remnants of heavier elements in the universe, which was mostly made up of primordial components like hydrogen and helium. Because population 3 stars lacked heavy components, their light output was brighter and more intense than that of modern stars. Important details regarding the genesis of galaxies and the subsequent chemical evolution may be revealed by these old stars. The sighting of 13-billion-year-old galaxies with remarkably similar structures and forms to our Milky Way is one of the major findings of the JWST. These galaxies preserve the early phases of the universe by acting as time capsules. Their striking resemblance to our own galaxy calls into question preconceived notions about the chaotic and destructive character of the early universe. Dr. Lear says the JWST observations have fundamentally changed how we think about the early cosmos. These findings imply that some galaxies quickly reached a high degree of structure and development. These discoveries challenge accepted theories of galaxy formation and challenge our understanding of the richness and diversity of cosmic development. With every observation made by the James Webb Space Telescope, we are able to learn more about the enormous oceans. This groundbreaking tool keeps revealing the secrets of the edge of the cosmos, giving us amazing insights into our cosmic beginnings. Without a question, the JWST has transformed astronomy by expanding our understanding of the vast cosmos and challenging our current understanding of it. The James Webb Space Telescope is a major advancement in our capacity to explore the depths of the cosmos. Its sophisticated features, including as its big primary mirror and variety of scientific tools, allow for observations that were previously unattainable by human technology. The JWST is situated at 1.5 million kilometers from Earth at the second Lagrange point, L2, where it can maintain a stable orbit and stay clear of Earth's heat and light. By collecting infrared radiation, which may pass through cosmic dust and reveal celestial objects hidden from visible light, the JWST is able to investigate the development of stars and galaxies in the early cosmos. Images of galaxies that formed soon after the Big Bang can be obtained using the telescope. These observations shed important light on the circumstances and mechanisms that gave rise to the first stars and galaxies. Astronomers can investigate the chemical makeup of galaxies throughout cosmic time by using the telescope to analyze light from far-off objects. Scientists can follow the evolution of chemical elements from primordial hydrogen and helium to the heavier elements produced in star interiors and dispersed by supernova explosions by analyzing the spectral signatures of substances found in these old galaxies. The JWST is also essential for researching exoplanets, or planetary systems outside of our solar system. The telescope advances our knowledge of exoplanets' potential habitability and the mechanisms underlying their origin and evolution by using its formidable instruments to examine their atmospheres. In order to answer the long-standing question of whether life exists beyond Earth, this research is crucial. Beyond its scientific accomplishments, the JWST is a testament to global cooperation and engineering creativity. The telescope, which was created in collaboration with NASA, the European Space Agency (ESA), and the Canadian Space Agency (CSA), represents the dedication of the world's scientific community to expanding our knowledge of the cosmos. There were difficulties in the JWST's development. The JWST was first suggested as the Hubble Space Telescope's replacement in the 1990s, but construction was delayed by several years due to a number of technical and financial issues. Nevertheless, the successful launch of the telescope in December 2021 was the result of the persistence of scientists, engineers, and managers. In the future, the JWST is expected to keep improving our understanding of the cosmos. Astronomers will be able to study the weakest and most distant objects in the universe thanks to its exceptional sensitivity and resolution, which will help them understand some of the most important astronomical issues. These include the beginnings of planetary systems, the nature of dark matter and dark energy, and the development and evolution of galaxies.